Okay, we're going to talk a little bit about what we call an electron configuration and how we can write what we call an electron configuration to show where the electrons are in a given atom. So we kind of learned about this already in chapter 2. So this is our quantum mechanics coming back in. We know that our electrons exist in orbitals. If you remember, the orbitals hold 2 electrons. We have subshells, and each subshell has a certain amount of orbitals, etc. Okay, so let's talk about hydrogen real quick. So hydrogen we know is, oops, didn't mean for that to happen, but that's okay. Hydrogen is the first element on the periodic table. So go ahead and take your periodic table and look at it. And it only has 1 electron, right? So we can represent that 1 electron. We know it's in the first shell because that's what gets filled first. And the first shell only has the S subshell, and that 1 electron will fall in that S subshell. So this here is shell number 1, the S subshell, and 1 electron is in that S subshell. So we would write that as 1s1. That is the electron configuration for hydrogen. Okay, let's talk about helium. Let's look at the same idea. I'll talk about the rest of this in just a moment. But helium is the second element on the periodic table. It has 2 electrons. Now, when we start filling our shells and our subshells, again, we're always going to start with the least energetic, so shell number 1 first. And then the shell number 1 only has the S subshell, and the S subshell can hold 2 electrons. So I see this for helium, the electron configuration is going to be 1 for the shell, and then S, because it's the only S1, and then both electrons will go in there. Remember, our S subshells can hold 2, our P subshells can hold 6, D can hold 10, and F can hold 14. Now, I can also represent this in what we call an orbital diagram. The orbital diagrams are simply showing, it's a little box over each shell and subshell. So for shell number 1, I only have the S subshell, and it can hold 2 electrons. So I'm going to represent them. Each one of these arrows represents an electron. And this is where the spin quantum number came in. Our spin quantum number was either +1/2 or -1/2. So you could say this one's representing +1/2 and this one's representing -1/2. These arrows are always going to be opposite of each other, which is the plus and the minus. And that's just because of it being stable that way. Okay. Now, again, we have our electron spin, which was the quantum number was our ms value, +1/2 or -1/2. I guess here you need to probably remember too that each orbital can hold 2 electrons only. The S subshell only has 1 orbital because it can only hold 2 electrons. And so if we did it as the orbital diagram, you're just going to have 1 box here. Okay, this having them go in opposite directions, that's called the Pauli exclusion principle. Pauli exclusion principle says that no 2 electrons in an atom may have the same set of 4 quantum numbers. Okay, so looking at helium and hydrogen, all right, so helium and hydrogen both have, or let's just look at helium real quick. Helium is the shell number is 1, so here we go. Remember, shell n equals 1. L is 0. When L is 0, it's the S subshell. ML is our orbital, and then one of those electrons in here is going to have a +1/2 spin, and the other one will have a -1/2 spin. No other element is going to have these same quantum numbers. So That's why 2 we represent showing that the orbital has 2 electrons but opposite spins. Okay, so as we're going to look at filling these orbital diagrams, and it's actually super simple. It's going to look a little overwhelming, and our periodic table is actually going to combine with us to show how we're going to do this. So things to remember right now, your sublevels. All right, so we know that we're going to start in shell number 1. Shell number 1 only has the S subshell. Then we'll move to shell number 2. Shell number 2 only has S and P. Then we'll go to shell number 3, and 3 has S, P, and D. And you'll fill them in those orders. So if you have 10 electrons, you're going to start by filling the 1s subshell. Then you'll go to the 2s subshell, then the 2p subshell, and then to the 3s subshell. So to just remember when we're talking about energy that S is the least energetic, then P, D, and F. So if you have a shell that has multiple of these, you're always going to fill the S subshell first. Okay. Orbitals that fall in the same subshell. So let's say we have a 3p subshell. Those, if I have 3p, P can hold 6 electrons, so they're 3 orbitals. Okay, each one of those 3 orbitals have the same energy. And there's a word for that, and it's called degenerate. So let's look. Here we have an orbital diagram. So this is increasing energy, as we know, because we're getting further and further away from the periodic table. This would be an orbital diagram where you would go ahead and put electrons in for a given atom. So, and you can see here, we're going to fill 1s first, then 2s, then 2p. So there's 3 orbitals in the p subshell, because p subshell can hold 6, and there's only 2 electrons per orbital. Then 3s, then 3p, then 4s, and actually it goes to 3d next. And we'll talk about why that is and use that a little bit later. Okay, so we have a rule here, and this is simply saying that as we fill electrons in our orbitals, we're going to start with the lowest energy and move to the highest. Okay. Shielding and effective nuclear charge. Effective nuclear charge is definitely something that is a trend that we're going to look at. In a multi-electron atom, so you're looking at anything over hydrogen, each electron experiences an attraction to the protons in the nucleus, and the closer they are, the better the attraction. And then they're also experiencing repulsion by other electrons in the atom. So if you have, let's say, 2 electron, or let's say the 2p subshell. The 2p subshell has 6 electrons floating around. Those 6 electrons are attracted to the nucleus because of opposites attract, but they're also repelling each other, right? The repulsions cause an electron to experience a net reduction in attraction to the nucleus. So the more repulsion they have, the less they are attracted to the nucleus. That is called shielding. The electron is shielded from the nucleus. So if we were to quantify this in a number, which we're just going to look at a trend, but if we were to quantify this in a number, we would have a number, and it would be that would be our effective nuclear charge. So how much shielding is going on. Okay. So here you go. The closer an electron is to the nucleus, the more attraction the electron experiences from the nucleus protons. And we're well aware of that, right? So the electrons in shell number 1, they're more attracted to the nucleus than shell number 2, just because they're even closer. Attraction between nucleus protons and orbiting electrons is related to the orbital type. So here, electrons in the s orbital are better shielders than electrons in the p orbital. And that's just because they're closer. They're lower in energy, they're closer to the nucleus. Okay, so moving on a little bit here, we're going to look at writing the electron configuration for some of our atoms. So again, we're always going to fill our electrons from the lowest energy to the highest. So we have S, and when we're talking about our subshells, S will be filled first, then P, then D, then F. Okay, so let's look at lithium. On your periodic table, lithium has how many electrons? It has 3. So I have 3 electrons to fill. I'm going to fill them first in the 1s subshell, because that's always going to be my first one. And then, so I can put 2 of them in the 1s subshell, and then I have the 2s subshell is next, and I have 1 more remaining, and can I put 1 electron in an s subshell? I sure can. So that's where it's going to go. So the electron configuration for lithium will be 1s2, 2s1. 1 being the first shell, and the s subshell, 2 electrons in it. Second shell, s subshell, 1 electron in it. And I can also show this as an orbital diagram. Now, as we're filling these, if we go down here, hide that real quick. If we go down here and see carbon, carbon has 6 electrons. So 2 are going to go in the 1s subshell. Then we go from 1s to 2s and put another 2 there. It maxes at 2, right? After 2s, I'll have 2p. Now I have 2 remaining, and I can certainly put 2 in the 2p. I can put a total of 6. But I only have 6 total here, so there's only 2 to put in there. All right, if I were to write the orbital diagram, I'm going to fill the 1s first. So you got 1 going up, 1 going down, then the 2s, and then we hit the 2p block. So 2p, remember, has 3 orbitals, and each block shows that. But I only have 2 electrons. So when we fill our electrons, when there's more than 1 in that block, we put 1 electron in each block at a time. All right? And that is what we call Hund's rule. So Hund's rule is when we're filling our orbitals, they have the same energy, they're degenerate. So we place 1 electron in each orbital before we start pairing them up. So if I had another 4 electrons, or excuse me, if I had another 2 electrons, I would put 1 right here. And then I would come back over here and fill it and pair this up. So you'd have the 1 going down. Okay, so here's just a summary of filling electrons in our orbitals. And let's go through it. Electrons occupy orbitals so as to minimize the energy of the atom. So we fill our lower energy orbitals before our higher ones. Each orbital can hold 2 electrons, and those 2 electrons need to be opposite in their spin. That's Pauli exclusion principle. When orbitals have identical energy available, so this would be like the 3 orbitals of your p subshell, electrons first occupy the orbitals by singly, and we don't pair them until we have to. And that is Hund's rule. So we're going to go ahead and do an example. So take a moment and go ahead and write the electron configurations for each of these atoms.